welcome to the lecture 41. We have been working with the spin stabilization. We will continue with this. So, last time we have derived these two equations. So, what we have done that theta 1 and theta 3 we have converted in terms of alpha 1 and alpha 3. So, the difference between theta 1 and alpha 1 it is not very large, okay, but thereby we have been able to eliminate the periodic coefficients from the equations for the differential equation for which was involving theta 1 double dot and theta 3 double dot. So, these things we have eliminated. Now, these two equations it is quite easy to solve. Let us first write it in a matrix format, so that we can discuss few things. Okay, the first term this alpha 1 alpha double dot and alpha 3 dot, we can for the first equation we can write this. You can see that if we multiply this matrix, so it will come as alpha 1 double dot, which is in the first equation. Similarly, we should get this term. So, here we will have minus 1 plus k times omega s plus 2 omega 0. Okay. Here this multiplied with this becomes 0. So, only this term remains. So, we recover this term here, and similarly the third term we need to get here. So, for the third term we will write here in this place. So, this is 3 k minus 1 omega 0 square minus 1 plus k omega s 0, and then we will have alpha 1 alpha 3 this equal to 0 on the right hand side. So, if we multiply we recover this particular term here. The same way we can get for this equation. So, they can be combined together. Okay, so, combining this, so already we have written for this part alpha 3 double dot. This part we need to write. So, this is 1 plus k omega s plus 2 omega 0, and this entry will be 0 here. Here in this part we will have 0 here as this entry, and this part will be minus omega 0 square So, if we look into this equation, so it appears something like A times plus B times d x tilde by dt plus C times x tilde, where equal to 0, where x tilde is alpha 1 alpha 3. So, as far as this equation is concerned, so this equation can be written in this format, and we will discuss about this particular one. So, we write this as x tilde double dot plus b times x tilde dot plus c times x tilde, this equal to 0. So, for a spring mass damper system, if you remember that for the spring mass damper system, the equation appears in this format. B times C times x tilde. So, it appears in the same format, but there is a difference. Okay. This term in the this is for the spring mass damper system, the spring mass damper. So, this B term is indeed this is the dissipative term. Okay. So, because of this the system will continuously lose its energy, okay, because of this term, because it is a dissipative term. Just like in the spring mass system, you have a mass hanging over, and so this is the mass. So, for this you can write this equation, this is the k, the spring constant for this, and damping coefficient we can write as B here. Okay. So, how do we write this equation? M times d square x by dt square, this we write as minus k x minus b times x dot. So, this is b x dot plus k x, this equal to 0. So, this tilde we should not put here, tilde we are using only for a vector. So, ultimately this is these two equations they look similar, but there is the difference that this is a dissipative term, while here in this case if you look here in this equation. So, this part, this is not dependent on the alpha 1 dot, this is alpha 3 dot here, okay. This is not alpha 1 dot. Had it been alpha 1 dot, then we can say that this is a dissipative term if this is a plus with a plus sign. If it comes with a minus sign, then it becomes opposite of that. Okay. But here the because of this presence of alpha 3 dot, this acts like not like if it is not a genuinely dissipative term, but what we call this as this is called the gyroscopic coupling. Now, let us look first into the just spring mass system. Okay, so, if we write equation for this, we write it like this, and for we know that this kind of system it is stable in the sense of Lyapunov, stable in the sense of Lyapunov, or we call this is statically stable. This kind of system it is also called it is a marginally stable. Why we are calling this as the statically stable? Because as soon as you displace this system from this position to say some other position here, okay, it is a displaced here. So, immediately a restoring force is generated. So, earlier also we have discussed that say if I have a ball like this and in there we are putting a ball. So, if I displace it here, so immediately the restoring force is generated. So, similarly here once I am displacing it, so the restoring force is generated. So, this kind of system we say that it is a statically stable system, and in a broader sense we call this is stable in the sense of Lyapunov. Now, you might have heard or you might not have heard about the Lyapunov stability analysis, but it says that if a system let us again take for a simple case, like I have a pendulum here, and this pendulum if I displace it here in this place. Okay. So, over a period of time this pendulum will oscillate and it will come back to this position. So, what is happening exactly? This comes to this position over a period of time because of the presence of this particular term. Okay. This is a dissipating term. So, here it continuously loses its energy and therefore, it returns back to the original equilibrium position. So, this kind of system we say this is asymptotically stable. Asymptotically stable means as t tends to infinity, okay, your disturbance, let us say this is the theta or delta theta, this is the disturbance you have given. So, delta theta this will tend to 0, means it will return back to the equilibrium stage, okay. and equilibrium already we have defined. This is defined as the stationary state of a system. Okay. So, this system is asymptotically stable. This system is also asymptotically stable because there is a damping term present here, but here the system we are discussing, there this is the gyroscopic coupling term, this is not the actual damping term. So, this type of system, this is not asymptotically stable. Okay. In the asymptotically stable, there is a dissipation of energy, just remember. Okay. So, once there is no dissipation of energy, which is here in this case, suppose that this is a purely spring mass system we have written, there is no dissipation term present in this particular equation. So, what happens once you disturb it and leave it? So, theoretically it will keep oscillating for the whole life, assuming that there is no air resistance or there is no dissipation of heat in the spring. Okay. So, if there is no dissipation of heat in the spring, so we have the, or either the air resistance is not present. So, this dissipation term is absent, only these two terms are present here. So, this kind of system, it is called marginally stable, means the poles of this system on the real and imaginary axis if we plot. So, it will lie on the imaginary axis, and this will keep oscillating for the, theoretically this keeps oscillating for the whole life. Okay. But in reality, here for this particular system, it so happens that the energy dissipates and therefore, it returns back to. So, we need to add one particular term here, b times x dot, we have to add it here, okay, for making a real representation of the system, okay, though damper is not present. Okay. So, here if we are putting a damper here, so this is just a modeling of this resistance. Okay. Energy is getting lost into the this spring, and then the energy is getting dissipated because of the motion which is due to the air resistance. So, all those things can be modeled through the this b times x dot term. Okay. But in practical, many of the systems are such that if the poles are on the imaginary axis here, so they absorb energy from the environment and these poles move into the right half complex plane, and therefore, this kind of system mostly they become unstable. While here in this case, while we are discussing this, so this kind of system in practical sense, it will be stable, because once you disturb it, so it will oscillate and slowly energy will get dissipated in the spring and in the form of heat, and also there will be aerodynamic resistance, because of that the motion will die out. So, it will lose its energy. So, in the Lyapunov stability analysis, we define a positive function, say V x tilde, where x tilde is the state of a system. Okay. So, this system, this is greater than 0 for all x tilde is the x tilde not equal to 0, and V 0 this equal to 0. So, basically this is a positive definite function. And Lyapunov, in the Lyapunov analysis, so what is assumed that if I have this pendulum system, if I displace it, so it is going to lose continuously its energy. So, say here in this case I can write its energy V x tilde in the form of its kinetic energy and plus potential energy. Okay. Now, so over a period of time, so this will continuously decay. Okay. So, V dot x tilde is less than 0. So, we will say that the system is asymptotically stable. If V dot x tilde in any of the case it turns out to be less than equal to 0. So, it is a call stable in the sense of Lyapunov, stable in the sense of Lyapunov. Perhaps we may not get time to discuss about the Lyapunov stability analysis in detail, because there are many other topics are remaining, but I am giving you the idea. So, if your equilibrium position is here x tilde e, and you are disturbing this system from this position to this position. Okay. So, this is your x tilde t 0. So, this is your initial state. Okay. Once you have disturbed initial disturbed state, and if you leave the system, so thereafter the system remains within a bound. Okay. So, let us say this, I call this as the delta neighborhood, and then I draw another neighborhood. Say this, I call this is a boundary which I call the epsilon neighborhood. Okay. So, if I leave it here in this place, and this system, its a trajectory, it remains bounded, means it does not leave this epsilon neighborhood, then we say that this system is stable in the sense of Lyapunov, stable in the sense of Lyapunov. So, what we have observed that if this is the energy function, so energy function, if the energy is getting dissipated, means this should be dV by dt getting this, V is getting dissipated. So, it implies this quantity must be less than 0, okay, because it is a continuously decaying, but it so happens that sometimes it may not decay also. So, in that case we write this as dV by dt, this is less than equal to 0. Okay. And if dV by dt this equal to 0, means that your energy is not decaying at all. So, whatever wherever you have disturbed it, so that disturbance will not die out. Okay. So, it so happens with this kind of system that if there is in the theoretical system this particular equation, that if you disturb it, it will keep oscillating for the whole life in theoretical sense, but not in the practical sense. So, this kind of system will say that it is a statically stable or stable in the sense of, here we have written it stable in the sense of Lyapunov. Okay. While the asymptotic stability is different, it is a as t tends to infinity, delta theta tends to 0. Okay. And one more condition is there for the asymptotic stability, that it never leaves epsilon neighborhood bound. So, that means if you are looking for the asymptotic stability, so I will show it by some other color. Okay. So, if the system is asymptotically stable, so and you are leaving it here, okay, so it will never leave the epsilon neighborhood. Okay. And thereafter over a period of time it will decay to the equilibrium position. So, this is the difference. So, only convergence to delta theta tends to 0, this does not say that the system is asymptotically stable. This must satisfy this condition, that this trajectory remains bounded in the epsilon neighborhood. Okay. If it is not bounded, then it cannot be asymptotically stable. Okay. Remember, this is very important. If this leaves this boundary, this brown boundary, this trajectory goes out of this brown boundary, then the system cannot be asymptotically stable, even though the state finally comes to the equilibrium state. So, these two things are, I will wind up this part here at this stage and restore the what we have been discussing about. So, we have been working with this particular system. So, here B is not a dissipative term and C is a stiffness term. This is the stiffness, okay, because it arises because of the spring stiffness. Just like here, this is the stiffness term. So, same way here we have written is the stiffness term, while this is not a true damping term. Okay. This is coming from gyroscopic coupling. So, this is not a true damping term, and we should never be misled by this writing here it in this way, that this is a damping term, because in the damping it will explicitly depend on, here this should have been alpha 1 dot rather than alpha 3 dot, which is not here. So, this is not a damping term, rather this is just a gyroscopic coupling. Okay. So, now we move to the other part. So, now we will look into the stability part of this. So, for this particular equation, we go back here and look here in this part. So, for the stability, what is required? That C, this C is a matrix. Okay. C is a matrix. So, this matrix should be greater than 0, means it is a positive definite matrix. So, your C matrix it is appearing like this. Let us say we write this as K 1 and K 3. Look here in this place, this term we can write this as the K 1, okay, and this particular term we can write as K 3. Okay. So, if we write it this way, so this is must be greater than 0. If we write it like this, so this implies that this is a positive definite matrix. This should be a positive definite matrix. So, and for positive definiteness, what is required, that K 1 should be greater than 0 and K 1 0 0 K 3, this determinant this also should be greater than 0. That means, all the principal in any matrix, if we are working like this. So, all the principal minors should be strictly greater than 0, greater than 0. So, if this condition is satisfied, then we say that the system is dynamically system is statically stable. So, why we are telling that? Let us look through this. Let us say there are two spring system and we write it like this. And if we try to combine it together, so how it will look like? Okay, 1 1 0 0 and here x 1 double dot x 2 double dot plus here we write here k 1 and this we write as k 2. So, k 1 k 2 0 0 x 1 x 2. Obviously, here in this case it is a decoupled, okay, but we can get the stability notion from this place. So, for stability what is required? This will be stable in the sense of Lyapunov, as you know that the poles are lying on the imaginary axis. So, or we said this is statically stable. Okay. So, if this sign is plus here, okay, only then this will be stable, otherwise it will diverge. If there is a minus sign here in this place, so it will diverge. Similarly, here there is a minus sign, it will diverge. So, what is required, that both these signs should be positive. Okay. So, that implies that not only the k 1 should be greater than 0 and k 1 k 3 is also greater than 0. So, if you look from this place, this implies this k 1 k 3 is greater than 0. So, k 1 is greater than 0, so k 1 is greater than 0 here and k 3 is greater than 0. So, this will be satisfied because k 1 has to be greater than 0. So, this will be satisfied only if k 3 is also greater than 0. So, these two things or I will make here the x 3 and k 3 x 3. So, that it looks same. Okay. So, from this place it is clear that k 1 and k 3 must be greater than 0, and if we look through this part. So, here also this says that k 1 should be greater than 0 and this quantity should be greater than 0, which gets reduced into this format, which gets tells that k 3 should be greater than 0, which is indeed the thing. Okay. So, if your C matrix is positive definite, then your system will be statically stable. This is one way of saying it, otherwise you say that it is a better to say it is a stable in the sense of Lyapunov. Okay. It is a more appropriate to say that a stable in the sense of Lyapunov, because it is a dynamical system. Okay. Static stability, it is always related to that the restoring force is available, it conveys only that meaning. Okay. So, this system is stable in the sense of Lyapunov. So, now we go back to this part. So, here if C is greater than 0, so if this part, this particular matrix, if this is positive definite, then we get but system which is stable in the sense of Lyapunov. Okay. Okay, but this part we will discuss little later on. So, for this we need to define those conditions. Okay, similarly, okay, we will take up the details later on. Let us first discuss this part. So, this is our B matrix. Okay. So, this is B matrix. Now, it so happens that even if your system is statically stable, means this term is not positive definite. So, we will continue in the next lecture. Thank you very much.